Welcome to the 6th lecture of the mini course in a dynamical system approach for Lane-Emden type problems. Annuli and exterior domain solutions. A solution in annulus or exterior domain solution is a solution U of Pucci plus or Pucci minus defined in an interval A rho for a positive real number and rho positive real number plus infinity, verifying the Dirichlet condition U of A equals to 0. Looking for this type of solutions, we approach the initial value problem P, which is the expression of Pucci's operator in radial form as U2 prime is equal to M plus minus of the expression inside, and U of A is equal to 0, U prime of A is equal to delta, a velocity, initial velocity at A, with delta positive. The problem of existence of solutions in the exterior domain for Pucci's operator was tackled by Galisi, Jacopetti, Leone in JD 2019, where they proved the existence of exterior domain solutions, and Galisi, Leone, Pacella, CPDE 2017, where they proved the existence of positive solutions in the annulus. And in Maia, Nornberg, a preprint of 2001, the weighted solutions and in annuli and exterior domain. For any P bigger than 1 and for each velocity delta positive, there exists a unique solution of the ODE problem, U delta, defined in the maximal interval, A rho delta, where U is positive and rho delta is bigger than A from the ODE theory. If rho delta is plus infinity, we get a positive solution in the exterior domain of the ball BA. In the second case, a positive solution in the annulus. A rho delta is produced. Note the equations are not invariant by rescaling. Once we rescale the solution, the annulus changes interior radial and exterior radial. Then we come up with the following theorem for Pucci's operator with weight. For any P bigger than 1 and given A less than B positive numbers, the problem of Pucci's operator plus minus has both a positive and a negative radial solution in the annulus AB, the weighted Pucci problem. Remarks: positive solutions obtained in the annulus for P plus or P minus may not be radial, since the Guidasny-Nirenberg type symmetry result of Liu and Sirakov does not hold for annular domains. All results obtained for initial velocity delta positive will also be true for negative velocities. Indeed, the negative shootings for an operator F can be seen as positive shootings for the operator G, defined as G of X big X as minus F of X minus big X, which is still elliptic and satisfies all properties we considered so far. In particular, the negative solutions of Pucci plus operator are positive solutions for Pucci negative in the same domain and vice versa. The first remark, important remark, which will have consequences later, is this one. All zeros of U are simple. That is, it does not exist a point R1 bigger than A with UR1 equal to U prime R1 equal to 0. This follows by the ODE existence and uniqueness with respect to initial conditions at R1. Since the function nonlinearity with weight H, S, R, A, S, P minus 1, S is locally Lipschitz continuous as long as P is bigger than 1 and R is bigger than radius positive A. Indeed, its derivative, take the derivative of H with respect to S, is going to be P R to the A modulus of S P minus 1, and this is globally bounded for any R between A and R1 plus epsilon. So the solution exists, is unique, and since with the information that UR1 is equal to, U prime R1 is equal to 0, gives the V equals to identically 0 solution, then the solution is identically 0 and cannot be a solution of our problem. The function U has at most one extremum between two consecutive zeros, a maximal point when U is positive and a minimum point when U is negative. Indeed, it's clear to see because if you take R0 with derivative equals to 0, a critical point of view, then the Pucci's equation is going to be m, some m plus minus u2 prime at R0 equals to minus modulus of u to the p minus 1 at R0, u at R0. So you see that the sign of u is related to the sign of u2 prime. So U2 prime R0 has the opposite sign of UR0. By the previous remarks, zeros cannot be of this type, UR1 equal to U prime R1 equals to 0. So if we are in a critical point of view, the U has a sign and it's going to give the sign of second derivative. Therefore, we're going to have when U is positive, the second derivative is negative, and when U is negative, the second derivative is positive. In order to approach our result, we had to define some energy functions and work with some energy functions for this problem. The first one is given in this proposition. For each delta positive and U delta solution of the initial value problem, we set the energy E sigma defined by this expression, U prime square multiplied by 1 over 2 RA plus modulus of U to the P plus 1 multiplied by this constant where you put sigma here, sigma positive number. Then if you take the energy functions defined in a step function as sigma equals to large lambda for U2 prime positive, and sigma equals to small lambda for U times U prime negative, this energy defined this way is piecewise monotone decreasing for intervals where you don't have a critical value. And whenever n tilde plus is bigger than 3 halves, which is our case because our n tilde plus is bigger than or equal to 2. To fix the ideas, let delta be positive and we take Pucci plus operator. Then we can write the expression for radial solutions in this way. U2 prime RA to the p minus 1 divided by some lambda small or lambda large, depending here. And then you have this quotient, which gives lambda small, lambda large, depending on the signs, times n minus 1 over r u prime. So this is the equation, the general equation for Pucci's operator in the radial form, where ms is the step function defined through ms of s as m plus of s, for s equal to u prime, as you see here, or u2 prime. Just a general expression for the expression we have been working with for Pucci's operator. Whenever u2 prime is different from 0. We know from the expression of m plus s before that it's a Lipschitz function. N hat minus 1 is going to be defined by this dimension-like number that appears in the equation. In either n, it's going to be n minus 1, n tilde plus minus 1, or n tilde minus minus 1, if u2 prime is different from 0. Anyways, when we took sigma equals to big lambda, this is going to be bigger or equal to m u2 prime when u times u prime is positive. This is just a matter of computation in the expression of the equation. And sigma equals to lambda minus is less than equal to m u2 prime if u times u2 prime is negative. Again, going to the equation, you can see this inequality. But in either case, we have this inequality. U prime positive, for example, divided by sigma is less than equal to u prime positive divided by m u2 prime, or for the negative case, we have the same. So we stick to this inequality in order to prove the monotonicity of the energy function. Let's take the derivative of the energy function in sigma. It's this expression, just take the derivative of its expression, and then we can substitute sigma by this inequality and use it here. So we have from here this inequality, and again, using this inequality above for the Pucci's operator in the radial form, we can substitute by this and end up with this product r to the minus a minus 1, u prime squared, a over 2 plus n hat minus 1. So the sign of this product depends on the sign of a over 2 plus n hat minus 1. If this is positive, then this derivative is less than equal to a negative number. And so it's negative. When is a over 2 plus n hat minus 1 positive? This is true, for example, when a is bigger than minus 1 and when a tilde is bigger or equal to 3/2. And we are in this situation when studying the Pucci's operator. These are our assumptions. Therefore, we have this term positive. Therefore, we have all this term negative, and we are done proving that the energy is decreasing. Proposition, let P be bigger than 1, be fixed, and assume that n tilde plus is bigger or equal to 3/2, which is natural for us because for the whole setting in our notes, we are with this bigger or equal to 2. For any delta bigger than 0, the local solution U delta of the initial value problem is extended to the whole interval a plus infinity. So we are showing this proposition that we have a solution in the whole segment of line from A on. To fix the ideas, we consider the Pucci plus operator. The energy ER is piecewise differentiable and continuous, strictly decreasing in each interval of consecutive extrema. At the zeros of U, the energy is continuous and strictly decreasing. Why? Because at the zeros, you don't have derivative equals to 0. So you have the energy well defined and it's strictly decreasing at those points. We claim that if U is oscillatory, that is, if U has infinitely many zeros, rho k, bigger than A, then necessarily the zeros go to plus infinity, and so U is automatically defined for the whole real line above A. If not, if rho k, the set of zeros, converge to a rho bar in 0 plus infinity, then by the mean value theorem, there would exist another sequence Sk of points in the real line between rho k plus 1, such that the derivative is 0. And so when you take the limit, you arrive at U rho bar 0, and the derivative is 0 because of these points. But this is impossible because rho bar would be the type of zeros that we have proven not possible in this situation. We then may assume that U has a finite number of zeros. In particular, it has a finite number of critical points, tau k, between these zeros. If the energy is bounded, this will imply that U is defined for all time, because then the ODEs has a nonlinear term which is bounded and then will exist for all time. By the monotonicity of the energy function, you start with energy at the A, its initial value. It's given by A large lambda because at this initial value, U times U prime is positive. So it's decreasing, therefore, in the first critical value, you have this inequality, but in the first critical value, this is defined by the other expression, E small lambda, in this way. E small lambda is also decreasing, so in the next root 0, you have the decreasing function, you have this comparison, and then you can go on comparing up to the last rho k. And then you have that the energy is bounded by the energy at the initial value A in the interval of R's, the maximal interval of definition of U. The claim is proved since the energy in its expression has U prime and U. So if this is bounded, if the energy is bounded, these two numbers are bounded, and therefore by the ODE theory, you have the solution for any real number R bigger or equal to A. And that's how we prove that a solution exists for all R bigger than A. It may change sign, but it exists for all R bigger than A. Then we can study, for example, the type of solutions we are getting for this shooting problem. For any delta shooting velocity positive, such that U delta is a positive solution of the initial value problem in the beginning of this lecture at A rho, with rho equals to rho delta, a real number, or plus infinity, there exists a unique number, tau of delta, where U prime tau is 0, which is a critical value for the solution U. That's what we are saying in this lemma. Previous, for R less than tau, the function U is increasing, and for R bigger than tau, the function U is decreasing. Let's see how to prove this. The proof is straightforward. Let us observe that a first critical point exists for U. To see this, we look for the dynamical system associated with this equation, Pucci's equation, and then you have variables x and z, as we have seen in the previous lectures. In this case, the behavior at the third quadrant for x and z less than 0 is given by x dot is positive and z dot is negative, with a blow up at a finite time such that U prime at this finite time e to the t is 0. Therefore, if we take tau equals to e to the t, this is going to be the radius where we find U prime at tau equals to 0. So it exists. The uniqueness of this critical value follows by the remark of extremes between two zeros given before. So if we have a solution in the annulus or in the exterior domain, it's going to be positive, and in between two zeros, you only have one extrema, which is a point of maximum. That's what we get in this lemma. Another proposition involves some energies, which are going to be used later, is this one. For any pair, delta and U delta solution of the initial value problem, the energy functions defined this way. E small lambda is the previous E small lambda multiplied by this power of R, and E big lambda is the previous energy big lambda multiplied by this power of R. Then we define these energies in different intervals. In the interval A, tau, which is the first and unique critical value, tau rho, the segment that follows tau, they are monotone increasing, where E sigma is the one we have defined previously. So, using these new energies, we produce energy functions which are monotone increasing for this problem. How do we use now these energy functions? Let's see, when delta goes to 0, the shooting parameter velocity goes to 0, what happens to the solution? Then we have the U at this maximum point goes to 0, and the point rho delta where the function has its other 0 goes to plus infinity. How do we prove this behavior? Using the energies. First of all, the energy A big lambda is decreasing. Therefore, for any R above A, we have this inequality. So in the interval A, tau delta, which is the critical value, we have this comparison of energies, and in particular at the point tau delta, we have this comparison. This is the interval where U and U prime are positive, so the product is positive, so the energy is given by E big lambda. Exactly at the point R equals to tau delta, which is the critical value, you have the same inequality. So we have this inequality at this point, and if we take delta going to 0, this gives us that U P plus 1 at tau delta, which is the critical value, is going to 0, 2. Next, we write the equation of U in this interval, A tau delta, as the radial expression in this form. So we can integrate from A to tau delta, and obtain the integral of a derivative is going to give these terms, and then you have the integral of the nonlinear term U to the P. So this is going to be 0 because you are at tau delta, and you have 0 equal to this difference. Taking the term, the integral term to the other side and dividing by A, you get that delta is given by this integral expression divided by A, and using that U at tau delta is less than equal to this expression in delta, we come up with this expression in delta with this power, 2p to the p plus 1. So dividing by delta to the other side, we obtain that tau delta to the power n tilde plus a is bigger or equal to a constant delta to a positive power. As delta goes to 0, this goes to plus infinity, and this makes tau delta go to plus infinity. But then, since tau delta is less or equal to rho delta, also rho delta goes to plus infinity as delta goes to 0. So now we have an idea on what is going on, what's happening to the solution, U delta, when the shooting parameter delta is very low. On the other side, when the shooting parameter goes to plus infinity, what is going to happen? When the shooting parameter delta is going to plus infinity, then rho delta, which is the next 0, is going to A, and U at its maximum point or its maximum value is going to plus infinity. Moreover, for every C0 given, there exists a positive constant, small c0, depending only on these parameters, such that if delta is bounded, then the rho delta is bounded above A. So this rho delta is well defined for deltas bounded, for shooting terms bounded. The proof of this lemma is complicated, it's long, it's included in our notes with all details, but basically depends on the monotonicity of the energy functions and eigenvalues of Pucci's operator. So the interested reader can go and see in details the proof of this argument, of this lemma. But with all this in hand, now we can approach the problem in the annulus. We fix the annulus AB for some internal radius A and external radius B. For every shooting parameter delta, recall that U delta is the unique radius solution of the initial value problem P defined for R bigger than A with a maximum radius of positivity at rho delta. Here, U rho delta is 0 if rho delta is a real number, a real radius, while U of R goes to 0 as R goes to infinity when rho delta is plus infinity. Then we can construct a mapping delta, shooting parameters delta, rho delta, which is the radius of maximum positivity. It is continuous by the ODE theory, continuous dependence on initial data. And then we can define a set of deltas like this. Depending on P, the power of the nonlinearity of the Pucci's operator, D of P is defined by all deltas such that rho delta is finite, is a number. This set is open by the ODE continuous with respect to initial data and is non-empty because we have shown that for delta very large, you are close, rho delta is close to A, so it's a finite number, and contains an open neighborhood of plus infinity because if delta goes to plus infinity, you have rho delta close to A, which is finite. Now, let delta star be the infimum of the unbounded connected component of D. So D could be this connected component or have different intervals, and we take the infimum of the unbounded connected component of D, the one that goes up to plus infinity. Since D is open, if delta star is positive, then rho delta is plus infinity. And we find this exterior of an annulus solution. If delta star is 0, then as delta goes to 0, this rho delta goes to plus infinity because it's pushed from below by the tau delta that goes to plus infinity. This is exactly the lemma that we proved when delta goes to 0. Then we have a function which associates shooting parameter delta with the radius rho delta. It's well defined and leads to an interval delta star plus infinity onto A plus infinity. By the second part of the lemma, which says that as delta goes to plus infinity, rho delta goes to A. Then there exists a delta such that rho delta is B, because B is a number bigger than A. And for this delta, we have found the solution in the annulus AB. For the non-weighted case, when A is equal to 0, Galizzi, Jacopetti, and Leone have shown that delta star is the infimum of D, so D is a connected component given by delta star plus infinity, is an open interval. Moreover, at delta star, they proved using energy arguments that you have a fast decaying solution in the exterior of a ball. When rho delta is equal to plus infinity, then we have an exterior domain solution in the exterior of a ball, and depending on its decay, it can be classified as fast decaying solution, slow decaying solution, or pseudo-slow decaying solution in the exterior of a ball. So a picture of all this is, for example, when P is equal to P star, the critical exponent, and we have a fast decaying solution. The regular solution is a fast decaying solution, is this red one, a fast decaying radial solution with this profile. And we have the green lines in our flow are solutions which blow up in minus infinity and blow up in plus infinity. This means that we have finite time, backward time, and a finite forward time, which are associated to finite radius, giving solutions in the annulus as the green one here in its profile as a radial solution. So the green lines in the flow with blow up backwards in time and forward in time are exactly the solutions which we have found by the ODE theory in the annulus AB. For P in pseudo-slow bigger than P critical, what is the scenario in the dynamical systems? We have a regular solution, which is pseudo-slow decay, is the red one, with this kind of profile. Then we have blue trajectory arriving at A0 and blowing up in finite backwards time, which means that there is a radius in the ODE, there is a radius from which this solution starts and then decays and is fast decaying at plus infinity. So it's the blue solution, the solution in the exterior domain. And the green lines are those which blow up in backwards and forward times, which means there are two radii, one smaller than the other, where the solution is a solution in the annulus as we have proven to exist. So this is the correspondence with the dynamical systems of the solutions we have been able to prove to exist by the ODE argument. Thank you for your attention and see you in the next lecture.